Hello there. In this video we're going to show why in the formula for the sample variance you divide by n minus 1 instead of n. So the sample variance can be thought of as almost the average of the sum squared distances of your data points from the sample mean. And the question is, it's almost the average because you divide by n minus 1, why n minus 1? Okay, to show this, we're going to prove that the sample variance is an unbiased estimator for sigma squared. Under these conditions, it's true under more general conditions. In a previous video, though, I showed, given this binomial setting, some things about the sample mean, the sampling distribution of the sample mean, meaning its expected value and variance, and we're going to be using that heavily in this proof. Okay, so there's a number of things that we'd have to see here to do this proof. First is, what is an unbiased estimator? What does that mean? Okay, so what that means is that the expected value of the sample variance is equal to the thing that we're trying to estimate, the actual population variance for this distribution. Okay. There's a number of seemingly unrelated facts that we need to know in order to get this thing done. We want to recall what the sample mean is by definition. It's the sum over all of your data points divided by the number of data points that you have. From this, we can see that the sum of our data points is equal to n x bar. This we're going to have to use. Next, the expected value and variance of any instantiation of this random variable. It should be equal to its mean, which in this case is p. We would also want, here I'll call this another point, that the variance of x is the population variance. And we get that by taking the expected value of x squared. This is just the definition of variance minus the expected value of x squared. Okay, we know that the expected value of x is mu, so we can call this mu squared, and we can get an expression here for the expected value of x squared is equal to sigma squared plus mu squared. This is very important. Additionally, we're going to need to know the expected value of the sample mean. The expected value of x bar in this setting, and I showed this in another video, is mu. The variance of x bar is the population variance over n in this setting where we're adding up a bunch of random variables and dividing by the number that we had to get the mean. This is how we get the variance of the mean, the variance of the sample mean. Okay, and we know that by the definition of variance, this is the expected value of now x bar squared minus the expected value of x bar squared, mu squared. And we can go on to say that the expected value of x bar squared is equal to the population variance over n plus mu squared. Beautiful. We've almost got everything we need to get started here. The last thing we need to see is, what is it? Okay, it involves the expected values and summation. So we want to see that the expected value of the sum of our xi is equal to, okay, well, let's just do it. What is this? It's x1 plus x2 plus all the way up to xn. Expected value of that. The expected value distributes. So we get the expected value of x1 plus dot 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 up to the expected value of xn Okay, but this is just n times the expected value of x, which is equal to the sum of the expected value of x from I equals 1 to n. So what I wanted you to see here is that the summation and the expected value can interchange, and this would also hold if it was the sum of the xi's squared. Okay, if we squared this term, all we would get is expected value of this thing squared plus this thing squared plus this thing squared, which is the expected value of this thing squared plus expected value, which is n expected values of the random variable squared, which is the sum from 1 to n of the expected value of the thing squared, or whatever it was. So we just want to see that these are interchangeable, whether it's x or x squared. Good, we're ready to actually begin the proof. I'll start off with something non-controversial. Surely you would agree that the sample variance, I might want to I'm going to write it here. Okay. Surely you would agree that the sample variance is equal to itself. Okay, very well. So this tells us that the expected value of the sample variance is equal to, and I'm just going to break this side down into the definition. I'm going to take 1 over n minus 1. This is our definition of the sample variance. 1 over n minus 1 sigma xi minus x bar squared. I'm taking this out of the expected value. It's a constant. And I get the sum of xi minus x bar squared. And all of that's in the expected value. Okay, and then I'm going to multiply both sides of the equation by n minus 1. So what I end up with is n minus 1 times the expected value of the sample variance is equal to the expected value of this sum, xi minus x bar squared. Okay, so what can we do in here? First of all, we need to just start dealing with this piece by piece. We're not going to get around it. We've got the expected value of the sum of, if we FOIL that out, we have xi squared minus 2xi x bar plus x bar squared. Good. We're going to distribute the summation over each of these terms, which we're allowed to do if we know our algebra of summation notation. I'm going to move this down here. So now we get the expected value. We have this piece, sum xi squared minus, okay, in our summation, x bar and 2 are a constant, so we get minus 2 x bar sum of the xi's plus, well, this is a constant. It'll come out of the summation notation, and we're summing from 1 to n, so you would just end up with n x bar squared. Okay, very well. This is looking a bit more manageable. Okay, before we distribute the expected value, I want to just see something in here. Before, we derived something about the sum of the xi's. Where was it? Ah, yes, it's n x bar. So here we can call this minus 2n x bar squared. Okay, now we're going to we've replaced that term. Now we're going to go ahead and distribute the expected value. So we get the expected value of the sum of the xi squared minus 2n is a constant, it comes out, expected value of x bar squared plus n expected value of x bar squared. Okay, the thing to do, I should have done it before this step, sorry, but we can combine these two. We have minus 2n times something plus n times something, so what we end up with is just minus n expected value of x bar squared. And now we've effectively reduced our problem to these two terms. Okay, well, we know that we can interchange a sum and an expected value, as we proved, or as we hoped to convince everyone of up here in point 6. So now we've got the sum of the expected value of xi squared. Okay, well, the expected value of xi is just an instantiation of x, so we can talk about the expected value of x squared, which we know is sigma squared plus mu squared. And we're summing from 1 to n, so we're going to get n of our sigma squared plus mu squared from this term. We can say goodbye to that. The expected value of x bar squared. Well, we know what that is too. We figured that up here. So we say minus n times sigma squared over n plus mu squared. Okay. I'm going to clear, no, I'm not going to clear space. I'm just going to like continue working this over here. So we can factor an n out of both pieces. We get n times, sorry, I want to make that really look like an n. We get n times sigma squared plus mu squared, right? Minus sigma squared over n plus mu squared. Oh, sorry. Very obvious what I did wrong there. We got the minus sigma squared over n minus mu squared. Okay, why? Because it was minus. Our mu squared plus and minus cancel, and we end up with n sigma squared minus sigma squared over n times n. Those cancel, and what we're left with is sigma squared times 1 minus n. Okay, and what did we say? What did we start with that we worked forward to algebraically to get here? Well, we started with this right here. So what we conclude is that n minus 1 times the expected value of the sample variance is equal to sigma squared n minus 1. And of course, drum roll please, the n minus 1's cancel, and we're left with the result we wanted, which is the expected value of the sample variance is in fact equal to sigma squared. Yay!